Okay, so let's get started. Uh, this is the first week of interactive live sessions for the course on fluid dynamics and turbo machines. This course is being offered by NPTEL and it's being instructed by Professor Shamit Bakshi and Professor Dhiman Chatterjee from the Department of Mechanical Engineering at IIT Madras. And Debjit. I'm a PhD scholar at IIT Madras and I'll be the TA for this course. So starting this week, every Saturday from 3 to 5, we will uh, meet in this Google Meet link and we will solve some problems together. So the main intention of these sessions is to enable a two-way conversation because the recorded lectures are sort of where we learn things, but those are one way. If you have any doubts or any questions or you have any problems in solving the assignment questions, then it's a good place to bring those questions and doubts up and even anything and not just doubts and questions, anything and everything related to the course can be brought up and discussed here. So that's the main intention of this platform. And with that, let's get started. So I have prepared some questions which we will be doing a back and forth. So I'll be sharing the questions. You'll try to read through the question and try to find the correct answers to them, and then we will discuss the uh, how to approach those problems and so on. So the main intention is not to test your problem solving abilities again. These are just to drive the conversation about the lectures that we saw in the first week, and it will be same for all the weeks going forward. So with that, let's get started. So this is the first question of today's session. It's a very simple one. So the question is, what is fluid dynamics used for? So as the title said, fluid dynamics and turbo machines. So why are we even interested in studying fluid dynamics in the first place? So is it option A, studying fluid flow patterns? Is it option B, designing new aircrafts? Is it option C, developing wind turbines? Or is it option D, all of the above? So it's a simple question, as you can see. Go through the options and pick the correct option that you think is correct. Then you can unmute an answer or you can type in the chat box, whichever way you feel comfortable. Then we shall, get rolling. Why study fluid dynamics in the first place? What does it help us do? Does it help us in studying fluid flow patterns? Does it help us in designing new aircrafts or developing wind turbines? Is it all of the above? Okay, so we have a response in favor of option A, that is studying fluid flow patterns. So let's take a look at the solution. It's actually not just A, so all of these are correct. So of course, it lets us study fluid flow patterns, but with the information and knowledge that we gain from those fluid flow patterns, we can apply that to a variety of problems. These are just two examples. So for designing newer and better aircrafts, we need to understand the aerodynamics of the uh, aeroplane as a whole. As we know, airplanes run on gas turbines. So for understanding the performance and make design changes to make them better, we need to uh, know a good amount of fluid mechanics. Then coming to the next one, so for developing wind turbines, so these mechanisms also depend a lot on the fluid mechanics around the blades of the turbines and so on. So for all of these cases and many more, uh, fluid dynamics, the knowledge and understanding of fluid dynamics is important. So the correct option for this question would be option D, all of the above. It's a simple one to get us warmed up and get started. If you have any questions, you can ask. If not, we will keep rolling. We will move on to question number 2 of today's session. So It's a match the following type of question. As you can see, there are two columns. So the left column has different physical quantities over there. So uh, option A is density and pressure, B is velocity, item C is stress and strain, and you have to match them with what kind of a field is it represented by mathematically. So the options there are one, velocity field, option two, scalar field, and option three, tensor field. So once you have matched the items in the left column with the right column, you will get a particular combination, and there are a few combinations given in the options below. So if you think one of them matches with that option, you can pick that. And as always, you can either unmute and answer, or you can type in the chat box as well. So we have one response in favor of option B, that is A2, B1, C3. So let's try to match them one by one. So the first one, density and pressure. So these are both scalars, and in a field, they would be represented by a scalar field. So A should match with 2. Then velocity, as we know, it's a vector, and in a fluid dynamic uh, system of thinking, they are represented by vector fields, because we're not worried about velocities of single particles or so on. It's a So we look at the whole domain, which could be 1D, 2D, or 3D, and we look at the uh, velocity field in that whole domain. And the last one, stress and strain, these are tensor quantities, and in continuum mechanics, be it solid mechanics or fluid mechanics, these tensors are also continuous fields, and they are represented by tensor fields. So C should match with 3. So A2, B1, and C3 should be the correct answer, which matches with option B. So let's take a look at the solution, and it is indeed option B. So good. Any questions on this or anything else regarding this? Yes.
I have a doubt, sir. Can you please talk more about this?
Okay.
Like,
Sure. So, don't think this is working. Can you speak again? Sorry.
No, no, actually, sorry. I got your question. I wanted you to speak because my headphones aren't working. It's my computer speaker. Anyway, sorry. So tensors. Basically, everything in every physical quantity can be thought of as a tensor. So tensors are the general mathematical framework in which everything scalars and vectors and tensors and order can be thought about. So tensors have something called order. Order meaning uh, how many uh, different features, or how many different parameters are required to describe a particular physical quantity. So if it comes to scalars, so only one number can you know accurately describe what a scalar is. So scalars are basically tensors of the zeroth order. So zeroth order tensor is a scalar. So it has just magnitude. Then comes tensors of the first order, in which you'll need both magnitude and direction. So uh, that's what a vector is. So vector. Then as we keep going higher up in the order, so stress and strain, these are of the second order. So these two, 0 and 1, they have specific names, scalars and vectors, because they are very common. Now, second, third, fourth onwards, they are all termed as tensors, and their order is mentioned. So the stress and strain belong to a class of tensors which are of second order. So in that case, uh, so there are three things now. One is, of course, the magnitude. Second is the direction, and the third new one comes in, that is the orientation. So as in a cuboidal, uh, in a Cartesian frame of reference. So if I'm talking about the uh, stress over here, I need to mention the magnitude, the orientation, as well as the direction. So now this has to be represented in a matrix. Now, if it is in 2D, it will be a 2 by 2 matrix. So, something like sigma xx, sigma xy, sigma yx, and sigma yy would be sufficient in 2D. Now, order and dimension are two different things. So, order determines how many, what can I say? So as you can see, so vectors will need only one row or column of items to properly describe them, right? It could be 2D or 3D. So it could be 2D having two items or 3D having three items, three entries over there. And a 3D tensor would similarly, again, has to be determined in a, has to be written in the form of a matrix, but the size would be determined by the dimension. So in that case, you would have sigma xx, xy, xz, and sigma yx, yy, yz, zx, zy, zz. Now you could have tensors of higher order, but for fluid mechanics, the maximum you need is a 3D thing. So for fields like magnetism and electromagnetism, they can have higher order tensors. So in that case, it would need multiple such matrices. So in that case, it would require something like a set of three matrices. So this would be a tensor of third order. Does that make sense, or is it still confusing? So we don't need to know very much detail of everything about tensor algebra or calculus, but we do need a little bit because it helps us write equations and so on, and a basic understanding of yeah. Not just dimensions, because I can have a 3D vector, right? It would have something like the u, v, omega. It's not dimensions, but how many. There should be a good word to describe this, but yeah, it's similar to dimensions. How many parameters do you need? So as you can see, this is just one row. This is something. So the size of this can be thought of as 3, 1. So it could be n dimensional. In that case, n cross 1. 2D or 3D, tensors of the second order, they would be n cross n. And similarly, of higher orders, when we go, it would be n cross n cross n, and so on. This number would keep increasing. Okay. Cool. So let's move along. We'll move on to question number 3 now. So here dimensionality comes into the picture. So I have given a velocity field over here. Velocity field v vector given by x, y, z into I cap plus x square j cap. So what is the dimensionality of this flow field? Is it a 1D flow field? Is it a 2D flow field? Or is it a 3D flow field? 3. Okay. So let's take a look at the solution. It is 3. Correct. So why is it 3? Right. So it's not I cap j cap that matters. What matters is whether the functions describing these components, what are they a function of? So velocity in the x direction, which is x, y, z, is actually a function of both, all three components x, y, and z. So that's why the dimensionality is 3. Correct. Good. Yeah.
Time is also great.
Hmm.
Will that be also included in the dimension, or we can?
Yeah, that's a very good and tricky question. So yeah, mathematically you can think of as time as in another dimension, but as we describe things, it's only the spatial dimensions that matter. And if time also comes in, we describe that as being steady or unsteady. So if it is a function of time, then it would be considered unsteady, and if it's not, if it's just x, y, z, then this is steady. And this would be 3D unsteady and 3D steady.
So if time is included, we call them as
Yeah. Yeah. So mathematically, yes, time is another dimension, but time is not like spatial dimensions. You can go back in X, go back in Y, but you can't go back in time. So yeah, it's a bit tricky. I mean, a lot of math and physics is involved there. We don't have to go to those depths. So as far as simple fluid mechanics is concerned, only the spatial dimensions are dimensions, and time just tells us whether the problem is steady or unsteady. Yes, good. Keep these questions coming. Very good. Now let's look at the next one. It's once again a similar easy question. So what is the correct dimensionality of this flow field, which is given by x I cap plus x square j cap plus x cube k cap? Is it 1D, 2D, or 3D? Okay, let's take a look at the solution. It is indeed 1D. Very good. So this is where many people get confused. They think that since velocity in all three directions are there, right? So in the uh, correct, correct. So although if I draw the velocity vector, it would have components in all three directions. So v vector would have components along vx, vy, vz, but they do not change with y or z. They only change with x. So they are only functions of x. I can write this as vx is a function of x I cap plus vy, which is also only a function of x j cap, and vz, which is also only a function of x cap. So in our analysis, when we do gradients and stuff, we don't have to worry about y gradients or z gradients. So dou y of anything, dou y of z of anything, these would all be 0 because the components aren't a function of y or z. So that simplifies our analysis to only a 1D problem, only in the x direction. So yeah, there's also a steady flow. There's no time anywhere. So if there was time, it would have been 1D, an unsteady 1D problem. Perfect. So these are very simple examples you are already aware of, but these are just to clarify some pain points which could be confusing. Anyway, very good. So let's move on. Move on to question number 5, which is again match the following type of question. We have two options each. One is Hookean solids. So basically solids and fluids, but particular types of solids and fluids. Solids which follow Hooke's law. Sorry, there's some noise coming in the background. Solids which follow Hooke's law, which are also known as Hookean solids, and fluids which follow Newton's law of viscosity. Newton's law of viscosity, also known as Newtonian fluids. So how are their stress and strain related? So sigma is the stress. These are common notations. Sigma is stress, epsilon is strain, and rate of change of strain with time. Dou epsilon dou T is also known as strain rate. So we have these materials on the left hand side and two relations connecting stress with strain and strain rate on the right hand side. You have to match the following, and there are only two options. It's either A1 B2 or A2 B1. Sorry. Hold on a second. Let me close my window. There is some noise coming from outside. Sorry about that. So what do you think? What would be the correct solution for this question? Okay, no problem. So let's take a look at the solution. It's actually A1, B2. So I'll just go back here. So solids, let's say I take this solid block and I put some stress on it. I apply, or I'll do this in the x-axis. So I squeeze it from both ends. I put sigma xx, sigma xx. This is the stress. Now, as a result, it would get compressed, right? It would become shorter in the direction I'm pressing it. Think this is a steel block or a rubber block which I'm pressing from both sides. So if the original dimension was L and this change in dimension, so let's say it became some L prime. So L prime would be smaller than L. L minus L prime, let's call it delta L. So another definition here is that strain is the percentage change or the fractional change in dimensions. So this is strain. So I applied stress, as a result some strain happened. Now what Hooke's law of solids tells us is that this stress that I applied, sigma xx, let's call it just sigma. It's some number, some, let's say 25 gigapascal or something. So what Hooke's law tells us is that this strain that I get would be exactly proportional to the stress. So the strain I get is exactly proportional to the stress I get. So if I apply 2 sigma, my strain would be 2 epsilon. If I apply x sigma, my strain would be x epsilon. It's a linear relationship. So that's what Hooke's law tells us. Now, things are simple for a solid, not so simple for fluids. So fluids might respond to this normal stress in a similar way, but if I apply a tangential force, or what is also in terms of stress also known as tangential stress or shear stress, so something like, once again I'll do it in this way, tau xy, which is similar to sigma xy only, but I'll just write sigma. Tau xy in this direction. I'm trying to shear it. So if it's a solid, then again it would just bend a little bit, and that would be it. And there also this shear strain would be proportional to the shear stress that I apply. But if it's a fluid, then some weird things happen. So if it's a liquid, let's say let's say I have some liquid between two parallel plates. The bottom one is fixed and I'm applying some shear stress on the top part. And this is like infinite in both directions. So infinite, very big two plates, and I'm applying some stress on the top plate. So here what happens, let's say what I start off as a line, this would first bend a little bit, then bend more, then bend more. It would just keep going. It would go non-stop as long as the stress is there. So, we can't really relate stress and strain, but rather the rate at which this strain is happening. So what Newton's law of viscosity tells us is that these two are proportional to each other. It's a strain rate in fluids that is proportional to the stress that is applied. So this is a very distinctive behavior between solids and fluids, and it's one of the primary definitions of what a fluid is in the first place. There is no finite strain, but a strain rate, a continuous strain which goes on. So connecting these, so Hookean solids would be stress proportional to strain, and Newtonian fluids would be sigma proportional to strain rate. So it should be A1 P2. So you have look at the solution. Yeah, it's A1 P2. Yeah. If you have any questions, go ahead, please. So you can imagine this, right? If I have two plates with some fluid inside, it won't stop after it moves a little bit. It would keep going as long as that force is there. Whereas if it's a solid, let's say I take my phone like this and try to share it, this may not change much, but if it was a rubber or something, it would change a little bit and stop there. It would generate internal stresses which balances out the external stress that I'm applying. But it turns out fluids can only generate this internal stress by continuous motion, not by a little bit of displacement, a finite amount of displacement. Yeah. Hmm. Yeah. Yeah.
It actually
Direction. Yeah. So in this case, I wrote sigma xy. Right? What it means is that this plane, this particular plane, its normal is in the x direction, and the force or stress that is acting that is in the y direction. So that's why the way to write this is sigma on the x plane in the y direction. First one is which plane or orientation. Which direction. So you'll notice here I don't sigma yx because it is this plane over here, which is the y plane, because the normal is in the y direction. But the stress or force that I'm applying, that is actually in the x direction. That's why sigma y x. Similarly, this one, this normal stress over here, that is in the x plane, in the x direction. The value would be negative because I'm compressing it, but direction, like notation wise, it will be x x y y. Like and so let's keep moving on. We'll move on to question number 6 now. So just a little bit of premise here. So we saw that Newton's law of viscosity told us that sigma is proportional to strain rate dou epsilon dou y. Dou epsilon dou t. Now the thing is, this epsilon can be written as velocity, some velocity into some time, which is the displacement, divided by the length in which this is happening. So just to make things a bit more clear, I have a block like this. This is delta y. This is the strain that happens. So this displacement is equal to the velocity into time, right? And we earlier saw that this is equal to displacement by whatever the original length was. So in case of shear strain, it is this length that we are considering, not along the uh, not this length, just to be clear. So epsilon can be written like this, and sigma, now I'm plugging this in over here. So what I would ultimately get is dou u dou y, which is the velocity gradient in the y direction. And you can replace this proportionality with an as an equation with the constant of proportionality. This thing is called viscosity or dynamic viscosity. This would depend from fluid to fluid. So things are all simple if this is this is Newtonian flow, a Newtonian fluid. Now all fluids are not Newtonian. There could be other kinds of fluids, in which case this is proportional to this strain rate to the power some index. Like this is to the power 1, but it could be 2, 3.8, things like that. So if n is equal to 1, we call them Newtonian. If it's not equal to 1, then it's non-Newtonian. So here are some examples of non-Newtonian types of fluids. And on the right hand side, we have some examples like toothpaste, paint, cornstarch, slurry, things we see in common day-to-day lives. So the types are dilatant, pseudoplastic, and Bingham plastic. And the examples are toothpaste, paint, and cornstarch slurry. So you have to match the two columns with each other, and once you find the right combination in the options given below, you can pick that option. Then A1, B2, C3. Okay, let's take a look at the solution. It's actually option C, A3, B2, C1, but let's go through each of these options carefully. So dilatant fluids are shear thickening fluids. So the more shear we apply, the viscosity would increase. So basically, these are for n is greater than 1. Then pseudoplastic, these are shear thinning fluids for n less than 1. So the more shear we apply, they thin out. Their viscosity reduces. And Bingham plastic, these are weird kind of fluids. So it would behave like a solid for a while and then start behaving like a fluid if we keep applying some stress. So in the stress versus velocity gradient equation, Bingham plastics would be like, it would be straight over here. So some amount of stress has to be applied and then it would start behaving like a fluid. So this is Bingham plastic. Then pseudoplastic would be something like this, and dilatant would be something like this. So this is 1, this is 2, this is, sorry, I have A, B, C, right? This is A, this is B, this is C. And some common examples. So let's start with the last one. Bingham plastic, it would be toothpaste. So, I think Professor Bakshi went through this particular example only, that when the toothpaste is within the tube, or even when you like pour it out on your toothbrush and just let it be, it remains intact, just like a solid. But once you apply some force or stress, after a certain while, it starts flowing. It starts behaving like a fluid. So toothpaste is one example of Bingham plastic. Then pseudoplastic or shear thinning, that example would be paint. So paint, you know, when I'm applying a little bit of shear stress, it's very viscous. But if I'm like trying to spread it with a very large, sufficiently large shear stress, it sort of thins out and gets spread easily. And that's a like valuable property that I need for a paint because I want to spread it over, a large surface area. And dilatant fluids are what becomes thicker when more shear stress is applied. I'm not sure if you have seen those YouTube videos of cornstarch slurry being kept in a bowl, and if you punch on it, your fist won't go through because you're applying a very large shear stress. Your the strain it applies is also very high. But if you softly pour your hand in, it easily goes in. So it's so the shear stress, the internal stress that it applies back is low when this rate of strain is low and very high when that rate is very high. So that's a shear thickening fluid. It becomes thicker when more shear is applied. So the correct order should be A3, cornstarch slurry, B2, and C1, which is option B, option C. Any questions on this? Yeah. Mm. Yeah, I think so. Okay, no problem. I mean, these are simple stuff. You can go through them, and now once you have these questions in mind, then if you go back in the lectures, maybe you'll be able to catch things better. Yeah. Yeah, much easier. Yeah. So hope that helps. So just to get to know you a little bit. So have you taken a course on fluid mechanics before, or so? Okay. 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 Ah, nice. Okay. Mm-hmm. Yeah. That's great. I mean, you could take a simple fluid mechanics course as well, but yeah, in this course also, this would also be helpful because the entire first half of this course, so there are like 8 weeks of lectures, right? So the first 4 lectures are on fluid mechanics only, and in the second half we will get into turbo machines. So these first 4 lectures should give you a solid feel for fluid mechanics. No puns intended. Uh, what is what fluid dynamics and what? Yeah, they're the same. So the basic difference there is that mechanics is the broader umbrella under which two things come in. Uh, so mechanics is the broader category under which two things come in. One is kinetics, in which we only worry about motion. So only velocities, displacements, that's all. Acceleration, that's all. And the second part is dynamics, in which we try to relate the motion with the forces. So this is only the study of motion, and dynamics is the relationship between force and motion. So basically the same thing. We never learn fluid kinetics alone. So usually in a larger, a longer fluid mechanics course, it would start off with kinetics and then move on to dynamics. These are just terminology. Dynamic fluid mechanics with dynamics are the same. So there are plenty of good books. So to get started with, it would be better if you take like an undergrad fluid mechanics course. So in mechanical engineering or chemical engineering or stuff like that, in the undergrad, a good book would be maybe Frank and White is a good book. Then Frank and White, yeah, fluid mechanics. I don't remember the exact name. Then by Indian authors is a very good book by Som Viswas and Chatterjee. It was Som Viswas and Chatterjee. That's also a pretty good book for undergrad level fluid mechanics. Then I'm trying to think what else. Yeah, these two should be good to start off with. I'll see if I can find some other. There's a book by T.S. Massey as well, but that could be a great advance. Like there is a uh, I would suggest you get started with either Frank and White. Oh yeah, another good book is by Senjal. Senjal. Then this is one by some Indian authors, Tom Viswas and now Chakravarti. Sorry, Senjal is also a foreigner. Yeah, you know Senjal. So these three, any of these three should be good enough. You said you're from math background, right? Yeah. So you'll have fun in fluid mechanics because there's a lot of math here. Yeah. Mhm. Perfect. Okay, so you probably know more math than I do. So later on, when we get down to the more difficult parts, you can help me out. Yeah. Yeah. Okay, so let's get moving. We have question number 7 now. So yeah, right now there's not much math because we are just starting off with an introduction to fluid mechanics. So there are these terminologies and jargon which we should get familiar with, and also a little bit of physics, which is just physics, not math. So unless we do that later on, we might bring up jargons, but if you're not familiar with it, it will be hard to follow. So once again, jargon question. I apologize. These are once again two terms. Exotropic. So these are types of fluids, just like we saw earlier, dilute and pseudoplastic. There are fluids called thixotropic fluids and euplectic fluids. And we have some common day-to-day examples on the right-hand side. Option 1 is ketchup, tomato ketchup, and yogurt. And option 2 is whipped cream. So once again, you have to match these two. I'll define these terms for you. So thixotropic fluids are fluids which become thinner if stress is applied over a long time. So they become thinner. if so, the main point is that shear is applied over a long time, or continuous shear is being applied. In that case, if the viscosity goes down, then it's called a thixotropic fluid. So if it becomes thinner, viscosity goes down. And rheopectic is if the viscosity goes up, it becomes thicker. So I have defined the terms for you. You think about the options. So ketchup or yogurt, if you keep stirring, does it become option A, right? Yeah. So let's take a look at the solution. It is indeed option A. So, you take a bowl of curd and you keep mixing with your spoon, it would, it would be pretty solid, well set early on, but after a while it becomes almost, like a liquid. You can drink it out of your bowl. So, same for the application. You see on the label, it would be written shake well before use. So once you shake it, it ultimately applies a lot of shear and it becomes easy to pour it out. So these are thixotropic fluids which become less viscous with shear force applied over longer time. Whereas whipping cream, so if you, I don't know if you have seen it. So if you whip cream for a long time, it sort of incorporates a lot of air, and you can almost lay it over like it stays whatever shape you give it like a solid. So it becomes very viscous. So whipped cream or whipping cream, that's rheopectic in nature. So the viscosity increases if you apply shear force for a long time. Okay. Any questions? All right. So yeah, here we have some math. So calculate the skin friction drag. I'll define what a skin friction drag is. For flow over a flat plate of area A, if the velocity profile of the boundary layer is given by this equation. So I'll draw a picture. So I have a flat plate like this, and I have some airflow coming from one side. So what happens is that this layer of fluid particles near the uh, flat plate. So okay, one question. So in math, you know what boundary layers are, right?
Yes.
So here, this is the fluid mechanics version of a boundary layer. It's a subset of the mathematical boundary layer. So there's more physics involved over here. So I'll talk more about that and less about the math. So the particles of fluid just sitting on the flat surface. So I'll take my phone over here and let's say I'm applying some. I have a fan blowing air on top of it. So the particles which are just sitting on this surface, they would stick to the surface and stay there. So the velocity there would be zero. But as we slowly go up, it would have some velocity. And ultimately, after a certain distance, it would be exactly equal to whatever velocity I was applying in the first place. So let's call that u infinity. So it would be, so if I, try to draw the velocity profile, this is my y-axis, and let's say I draw the velocity in the x-axis. So it would be zero over here at the wall, and it would slowly increase and become constant after a certain distance. It would be constant over here, slowly increase to that level. And so this thickness, this distance is called the boundary layer thickness. And if you imagine, so there would be one boundary layer over here, one boundary layer over here, and so on. So at every x location, there will be a boundary layer, and the thickness of that boundary layer grows like this. So it increases. So this is what the boundary layer is. Now, Maybe we'll go through boundary layer in one of the later lectures, but it's not there in week one. Don't worry. So all we need to know is that the velocity profile, this u as a function of y, can be written like this, equal to a plus b y over delta. Delta is this boundary layer thickness. It's just a number right now, by y over delta squared. So the question is, what would be the skin friction drag? Okay, another piece of terminology over here. So it's basically asking what is the force on the flat plate. So uh, I'll tell you how to do this. So you know the velocity. You have to find out what the shear stress is on the flat surface because of this. So there is some flow over this flat plate, right? So this air would try to drag the flat plate towards its own direction. So that force is called the drag force. So this shear stress multiplied by area would give us the force. So A is given. This is what you have to find, and that should give you the force. I'll just go through this. So my velocity is given as a function of y. I need to know what the, okay, another thing. So how do I find the shear stress? From Newton's law of viscosity, which says that, it's equal to the viscosity into the gradient. So I need to find dou u dou y. So I differentiate with y. Very simple math. This gives me 0 plus b by delta plus c by delta square into 2y. And this force is acting in this location over here where y is equal to 0. So this is at y equal to 0. So if I plug in the value of y, I will simply be left with b over delta. And I'll plug this in over here. So it's viscosity multiplied by b by delta. And the drag force would then be equal to tau into area. So this into area. That's it. So what do you think? Yeah, so the axis I can take anywhere, right? So my axis is fixed to the flat plate. So this is what my origin is. This is the x direction, this is the y direction, and it starts from the flat plate. Yeah, I should have mentioned where the origin is somewhere in the question, but this is like the convention. So wherever it is, you have to find it wherever that flat plate is. So that's why y equal to 0. All right. So moving on. So we have two pictures over here. So in fluid kinetics, there are these terms which are thrown around called path lines, street lines, streamlines, and so on. So have you gone through this part in the lecture? No, not yet. So then it would be a bit difficult, but anyway, let's go through this. So I have two pictures on the right hand side. The first one is a long exposure photograph of a campfire. So you must have seen this, right? So people increase the uh, exposure time of their camera to take pictures like this. There's another example where a car would be going in a winding road, and if you take a long enough exposure photograph of that, then the car won't be visible, but the line traced by the light is visible in the end. Have you seen something like that? Yeah. So this first photograph is something similar to that. So there's a fire burning, and if you take a long picture of that, the particles flying out of that fire, those traces are captured in the photograph. So that's the first one. And the second one is a smoke visualization experiment being done to find the flow over a car. So this is to test the aerodynamics of a car. So how aerodynamic is the design of it? So that would determine what that drag force is. And usually car designers want to minimize that so that less fuel is required and you'll get better mileage. So this is a second type of a flow where there's smoke coming out of this nozzle over here, and that smoke sort of traces a line like that. And this is the instantaneous photograph. This is not a long exposure photograph like the first one. Here, continuous smoke is coming out and it's tracing some shape. So so these lines and shapes that we see here, they correspond to some fluid kinetic concepts as well, known as path lines, streamlines, and streak lines. So yeah, you go through the lectures, then this will become clear, and these questions will also be, these slides will also be shared with you. You can go through them later. Right now, you can take a guess. Hmm. Yeah, 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 yeah. Mhm. So next week, try to watch, up until week 2, and yeah, then we'll be able to have a better. You can come up with doubts and questions. And you can always come back later, like yeah. So mhm, mhm, yeah, yeah, yeah. I understand. There is no pressure on you. It's fine. So once you go through the lectures of week 1, and if you have some questions, you can always come on in next week and ask them as well. You feel free to do that. Right now, let's take a guess. We need to go through this. So, no helplines available. Yeah, okay, no problem. Yeah, no pressure. Let's move on. So it's basically, yeah, option one, path lines and streak lines. Since we are here, I'll try to describe what these mean. So path line means that in a fluid domain, let's say I have a pipe like this, and there's some flow inside it. You can visualize it, a cylindrical pipe, and there's some water going through it. So now, and let's say this pipe is made of glass. I can see through it. I can take pictures with a camera. So now, let's say I put a red sort of dye, a drop of dye in there. I, put in some syringe and I release a little drop of colored water. So there's this red dye, a block of red dye, and using a video camera, I take a video of that. So it will, go through in some way. And from that video or from that series of pictures, if I connect all the positions that is traced by that small block, in different points of time, at t equal to 0, it was here. At t equal to t1, it was here. After a while, it was here. So if I connect all those dots, then what I get is called a path line. So as the name suggests, it's the path taken by one particle. And this picture is basically the same thing. So if I take a long exposure photograph, I'm basically recording all the points that is being covered by this one particle, which is emitting light. So these are multiple path lines of multiple particles coming out. So these are path lines. Now the next thing is streak lines. What are streak lines? So once again, I go back to my pipe experiment, and instead of just releasing one dot, I have something like this. I put an injector in, and I keep adding more and more of this colored liquid. So that colored liquid will now flow as well, and that would also trace some kind of a line. That is known as a streak line. These are the most common ways of visualizing flows experimentally. So that's what this thing does. So it releases some smoke, and it continuously releases smoke, and that smoke traces out a shape which sort of gives me an idea how the flow is actually happening. Then comes streamlines. These are a bit more tricky or mathematical. So let's say I have a flow field like this, a 2D flow field in X and Y, where the flow goes in this direction, like this. So a streamline is a line. It's the English definition of a streamline is that a streamline is a line in which every tangent at any point, sorry. So if this is my streamline, and at any point if I draw a tangent, then that tangent would give me the direction of velocity at that point. So that's what the definition of a streamline is. These are all different things in case the flow is unsteady. And if it is steady, then all of these sort of become one and the same thing. Okay, I won't go on any further. You go through the lectures, and then if you have questions, please come back. Okay. Yeah. So,
Next week.
yeah, same time. Same time next week. Okay, so, yeah. Were you saying something? So,
No, really.
yeah, no pressure. But right now, what I said, does it make sense even a little bit? Okay. So these are the physics or maths definitions of what these physics or sort of English definitions of what these lines are. There is a lot of math behind them. So given a flow field, find what the path line is. Given a flow field, find the equation of the streamline. Those things are there. Yeah, obviously. So you're learning it for the first time, you'll go through all that. No problems. Okay, so this last one, this will give you a feel of what I was talking about. So, so the velocity field is given by sorry, the velocity field is given by this equation, where velocity v is equal to e power minus x I cap plus e power minus y j cap. It's a 2D steady flow. Now, find the equation of the path line for a particle which has flown or which has flowed through x naught y naught at time t equal to 0. So let's get started. So this first component of velocity vx can be written as dx dt of a particle, right? That's what the definition of velocity is, and that is equal to e power minus x. Similarly, Vy is equal to dy dt of again the particle equal to e power minus y. Now we'll integrate these and try to find out what x is. So I'll have e power x dx equals dt. It will simply be e power x equal to t plus some constant c1. And I'm not doing it, but same thing for this. It will be e power y equal to t plus c2, another constant. And let's write y is equal to log of t plus c2, and x equal to log of t plus c1. Now, another piece of information is that at t equal to 0, it has passed through x naught, y naught. So if I put in t equal to 0 over here, my c1 would be e power x naught, and here my c2 would be e power y naught. And that should give me x equal to log of t plus e power x naught and y equal to log of t plus e power y naught. Now, one second, you're a math guy. You don't need to. I don't. You don't need me to tell you this, but you can keep it in this parametric form, or you can eliminate t and write a cleaner version of this equation. So if you eliminate t, then this becomes, you know, so e power y is equal to e power y naught. So basically, t is equal to e power x minus e power x naught equal to e power y minus e power y naught, and this would be the equation of the path line. So I can draw this now in the xy plane. I don't know how this function might look like, but it's a function of x and y. So let me try to think. E power x. So this is basically like saying, can you help me out with this? So it's basically e power x minus e power y equal to some constant. I believe it will be something like this. Like a hyperbola, not a hyperbola, but something like that. Or no, there's a minus sign, right? Mm,
from the negative x.
why? Yeah, that's what I was thinking. But there's this negative. Mm, yeah. Anyway, you get the point, right? There will be some. Yeah, that's a fixed point. So basically, yeah. Yeah. hmm Yeah. So it would be something like this. Okay. So let's say I start from here. Oh, negative x. Sorry. Sorry. I think this should be it, right? Yeah. Mm. Sorry. So let's say, so basically, let's take these two things: x equal to log of t plus c1 and y equal to log of t plus c2. Oh, sorry. There is invisible. It's my last thank you slide. I'll use that for. So x is t plus some constant. Y is log of t plus some constant. So in the positive xy plane, let's say I start off on somewhere here, which is x dot y. So with increasing t, both x and y would increase, right? And the rate of change would also be the same. So it would be something like a linear curve. It would gradually slow down, but the direction should be something like this only. Does that make sense? Log is an increasing function, and with t, it would keep increasing, and the rate of increase of both x and y would be the same. So it should trace out a straight line like this. Because let's do this thing. So let's go back. So dx dt is e power minus x, dy dt is e power minus y. So if I divide them, dy dx would be e power minus y by e power minus x. Okay, no, yeah, true. So for x naught, y naught exactly equal to each other, it would be a straight line. Otherwise, so if y is higher than, so the gradient is e power minus y by e power minus x. So if y is greater than x, then this value is less than 1. My guess is something of this sort. So, see, if x and y are exactly equal to each other, then it would be a straight line like this. If y is greater than x, then the gradient would be less than 1. So less than 45 degree, something like this. And if y is less than x, then it would be something like this. See, this is how engineers butcher maths. Sorry for that, but let's Google this. There are plotters and all, right? I'll stop sharing and plot of e power minus x minus e power minus y equal to. Yeah.
Okay, it would be something weird like this. Can you see the plot? Yeah, you were right about things being only in the negative x. But I think if I keep changing that size, it would show up different plots. So this is for the constant being equal to 5. Now, if I change that constant, yeah, where did my thing go? If I put this equal to -5 now. Uh, it becomes a straight line like this. I don't know if it's doing it correctly, but okay, anyway, this is not the point. Maybe I should pick examples within my mathematical capabilities. But the point is that you get a function of x and y, or you get a parametric form as a function of both x and y as functions of time. Either way, you can plot them and get the equation for the path line. So that's all for this week. We meet again next week. Thank you for joining and thank you for your interest. Bye.